Okay. Um, cool. All right, we're gonna go ahead and well, I guess I'll go ahead and get started. Just me in the Zoom call. So I've got like a little bit of a review planned here now. Um, since we're kind of night before, or probably some of you will be watching this day of. Hopefully you've been going through the old exams and you will be sort of familiar with some of these problems, and this review will serve to kind of organize those topics one more time, and also to talk a little bit about how to approach problems on an exam. The biggest change, obviously, from the semester to the semester, week to week, you know which topics are covered on which questions on the homework and on the quiz. On the exam, of course, first of all, they're not going to be in order. So you'll jump from, chapter 5 to chapter 2 and so on. There will also be some questions where there's a little bit of ambiguity as far as like which tools you can use to solve the problem. So I'm going to sort of just go through here, and I'm going to talk about some old exam problems for each of these topics. So the first thing that I want to talk about, this is hopefully a free point on an exam if you get a question on it, is a unit conversion problem. And the unit conversion problem that you've probably all seen is something about like Jupiter's day or something. They tell you that a day is I don't know, it's like 9 hours and 42 minutes or something. And they ask you how many minutes are in a week. Okay, so first thing you do is you need to convert this into minutes. You have hours and minutes here. So this would be equal to, 9 hours times 60 minutes per hour plus the other 42 minutes. So 9 times 6 is that 540 plus 42? So that'd be 582. So that's how many minutes are in one Jupiter day. This number's wrong, but whatever. That's how many minutes are in one Jupiter day. And then if you need to find the number of minutes in a week or in 2 weeks or in a month, you just multiply this number by how many days there are. If you have a more complex unit where you have, like for instance, let's say I want to go from 100, this is one that you might actually need to do, 100 kilometers per hour into meters per second. The way that I do it is I start by converting the top unit, and then I convert the bottom unit. We know that there are 1,000 meters in a kilometer, so you could say that'll be 10 to the 3 meters on top for 1 kilometer. Notice that'll knock out your kilometer units, and you'll have your meters up top as you need. And then if I need to go, from hours to seconds, I know that there are 60 times 60, or 3,600 seconds in 1 hour. And then that will knock out your hour units, and now you'll have meters per second. Once you do, what is 1,000 over 3,600? 1 on 3.6 times 100. Anyway, so yeah, that's unit conversion. I'm hopeful that if you do get a unit conversion problem on the exam, that will be an easy one to knock out. Talking a little bit about the way that I would approach exams, as I mentioned, the questions are going to be all jumbled up, and especially because the exam is online, the computer actually will randomly scramble them, I believe. So my recommendation would be to do a few passes through the exam. Usually when I'm taking an exam, my first pass through is maybe I will tackle half of the questions. Sometimes I'll just go through and read the whole exam and then go through and decide which questions to do first. But there will be some longer problems and some shorter problems. And especially if there's a problem type that you feel like you struggle with and you're able to identify that problem and not spend a ton of time initially, you can save that problem until the end and get the points that you have a better chance of getting. So unit conversion problem, that would be a good one to start with. Another problem is the direction problem, as I'm calling it. And the direction problem goes something like this. A guy starts at home and he walks 1 mile to the west, and then he walks 1 mile to the northwest, and then he walks 1 mile south. And they're going to ask how far from wherever he started does he end up, right? What is his net displacement, in other words? This is a vector sum problem. And, you can turn these into I hat, j hat, and k hat. The most important one here is the second one. I trust that everyone knows that 1 mile to the west would be, 1 mile that way. 1 mile south would be 1 mile that way. But to the northwest, the way that 1 mile is going to split up to the northwest is if your hypotenuse is 1 mile, you'd actually have components to the north and to the west. So whatever direction is given here, this would actually split up into 1 en route to north and 1 en route to west. So if it were southwest, it would be 1 en route to south and 1 en route to west. Okay, so that's how you're going to split up the non cardinal direction if you get this problem. And then once you have this, you can go ahead and just sort of sum together. You could do it as we usually do, like the x and the y, So if you have like your x and your y. So for the x, I have that 1 mile west right here. So that would be a 1. And then I'd add this 1 mile west, or 1 en route 2. So it'd be 1 plus 1 en route 2. And then for the y, I have this 1 mile south, since we're going negative y direction there. That would be a -1. And then I would have this 1 en route 2 north. So I just add 1 en route 2. And then, of course, how do we find the magnitude of a vector? You add these, you take these, you square them each, add them together. I don't have room for my plus sign, but you add them together and then take the square root. So we've done that quite a bit in this class. Okay, moving on to actual like vector. Let's see, do I want to do the vector? Yeah, I'm going to do the vector stuff first, and we're going to go back and do 1D motion. So we have 2 vector operations that we need to be responsible for. One of them is the dot product. The dot product, if you recall, A dot B, whoops, it's supposed to be a dot between. A dot B is equal to AX BX plus AY BY plus AZ BZ. And we saw last week our first actual, I believe we had our first application, our first physical application when we looked at the definition of work. Okay, so this is one definition for the dot product. The other side of the dot product tells us that A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle theta. Now, on your exam, you will likely, based on looking at old problems, and again, I should mention that I have not looked at this semester's exam, so this is just based on my reading of what the old exams look like. I probably need to legally say that so I don't get in trouble. Anyway, so historically what you needed to do is to set both of these definitions equal to each other. And so there are 2 problem types that you'll see on the old exams. One is the projection problem. And a projection problem says the component of A in the direction of B, for example. In that case, you're going to set these 2 equations for the dot product equal to each other. And then if I want the component of A in the direction of B, the component of A in the direction of B is just the A cosine theta from the second definition. And then I just divide the first definition by the magnitude of B. So I have the AX, BX plus, and so on. And I would divide by the magnitude of B. I can do vertical bars for both of these to say magnitude, but also the letter just tells me that's the magnitude. And so there you have it. A cosine theta is the component of A in the direction of B. So you just solve for this. That is the one application of the dot product, or one of a number that you are responsible for the exam. And another one that you'll see is the angle between 2 vectors. So if I need to find the angle between two vectors, and they give me, again, an A and a B, and A and B can both be three-dimensional vectors with an X, Y, and Z. If I want to find the angle between them, I could do it like graphically, but that would be very painstaking. The other thing that I can do that's more simple is I can just say that the cosine of the angle between them is going to be equal to the AX, BX, plus so on and so forth, divided by magnitude of A times magnitude of B. And so you'd calculate this thing in your calculator, and then you'd ask your calculator to take the inverse cosine, and that would give you theta. The other definition, or the other, I should say, vector product that we're responsible for is the vector product as a cross product. And I'm actually not going to speak a whole ton on this. The cross product is given explicitly on your formula sheet, and it seems, based on the old exam, that it's pretty common to just explicitly ask for that cross product. We haven't yet had any applications for the cross product in our physics studies. So for the time being, yeah, I'll just leave it at that. Just make sure you're comfortable using that equation. Okay, yeah, so let's go ahead and talk about motion. So we have 1D motion, first of all. And with 1D motion, there are three equations that are given. There are three kinematics equations given on your formula sheet. There are two that are not given on your formula sheet that I would recommend maybe spending a little bit of time memorizing, getting it into your head. And I would write these down, once you do your honor lock stuff, I would write these two down, and I'm going to give you one other thing to also write down in just a second. But I would write these down right away. Delta R is equal to V, that should be V final T, minus 0.5 AT squared. This looks like the one on your formula sheet. That's V initial T plus a half AT squared. And then the other one is that delta R, which is just a displacement. R is just a generalized position vector. Delta R is equal to V final plus V initial on 2, or initial plus final, times T, times time. So with the three equations that are on your formula sheet, and with these two equations, you have a set of 5 equations. Each of them have 4 of the 5 kinematic quantities. You determine which quantity you are unconcerned with in a given problem, and you choose the equation that doesn't have that quantity, and that's how you solve a 1D motion problem. A specific 1D motion problem to be aware of is a problem with gravity. With gravity, first of all, your acceleration is going to be negative 9.8. That's important. Also, you're going to have keywords like an object being dropped. If an object is dropped, its initial velocity is 0. Similarly to how in the x direction, if you start from rest, your initial velocity is 0. I think most students, it seems like, are starting to grasp that concept at this point in the semester. So that's very helpful. So this discussion here is for constant acceleration. If you remember, in order to use kinematics, we need constant acceleration. Let's say we have a case where we do not have constant acceleration. In that case, we're going to have to talk about calculus. So we have 2 ways that we have utilized calculus, both in motion and actually moving forward. We had some calculus problems this week on the homework and on the quiz. So if you're given a time varying function for the acceleration, let's say. So let's say I'm given some A of t. What I might be asked to do is to generate a position function, right? So in that case, I would say that V of t is equal to the integral of A of t dt. That should be dt, not dx. And then your acceleration with respect to time would be the integral of the velocity function. So you do 2 integrals in order to find the position, not the acceleration. Whoops. Position. Cool. So that's what you would do with an explicit equation. To go the other direction, if I were given some x of t and I needed to find something about the acceleration, I know that the velocity is equal to the derivative of position. And I know that the acceleration is equal to the derivative of the velocity. So this is how you would deal with an actual like function. Also, something that you are responsible for being able to do with calculus is turning those concepts into an integral on a graph or a derivative on a graph. So for instance, there's an old exam problem where you've got like something like this, and let's say they give you like point A, point B, point C, point D. Okay, I'm sort of making up my own version of this problem. This isn't exact. But yeah, so this would be like a position versus time graph. And they're going to ask you, where is the magnitude of the velocity largest? So the magnitude of the velocity is, let's say, just write out largest. So in that case, what we need to be able to do is to take a position versus time graph and relate that back to velocity. Well, I know the velocity is the derivative of position. And so since velocity is the derivative of position, then to turn that into something about a graph, remember the derivative is just the slope, right? So my velocity would be equal to my slope on this graph. So by asking when the magnitude of the velocity or the speed is largest, they're saying, when do you have the largest slope, either positive or negative? Well, A is near a slope of 0, C is near a slope of 0, D is near a slope of 0. B, though, you have this very large negative slope. And so, hey, there's where your speed would be greatest in this problem. The other type of problem that you'll have with calculus, if we're not reading off a slope, then usually we'll have a really nice geometric figure where they're very clearly demarcating sort of the lines. And of course, in this case, once I'm sort of at the point where once I see a figure that looks like this, that looks like something I could find an area of, immediately my brain is like, okay, how do I actually like do an integral on this problem? Because that's probably what they're about to ask me to do. So just remember that your integral is related to the area. And as long as you have that connection and can recognize the shape of a graph, you will be in pretty good shape with those problems, because those do tend to be area problems. Okay. Yeah, so the next thing I wanted to talk about was 2D motion. Here's our method for solving a 2D motion problem. One thing I do want to mention is that there is an equation called a range equation on your formula sheet. Sometimes people have questions about like exactly how to use the range equation. The range equation only works so long as you start and end at the same point. It's very rare that they'll give you a 2D motion problem where the range equation applies on an exam because it's an easy case. Essentially, the range equation falls out because your delta y, your displacement in the y direction, is 0. And so a bunch of stuff cancels when you go to do your kinematics between x and y. The general approach to 2D motion, is to split up into x and y. We'll call this step 1. Step 1 would be to list out your acceleration, initial velocity, final velocity, delta x in time, and do the same thing on the y side, acceleration, initial, final, delta y in time. Okay, so you list out all your stuff, generally in the first step. Second step then would be to do your kinematics, just like you do in a 1D motion problem. You do your kinematics for x and for y separately. And then the last thing is to, we'll call this step 3, to solve a system. You'll have a system of 2 equations generally, and here you'll solve a system of equations. Most important note here is that time is the quantity that links x and y together. So these 2 times are the same. Also, we've seen quite a few problems where the velocities can be linked together. So for instance, if you have, just going to sketch this right here, if you have an initial velocity at some angle theta, the x component is the initial velocity times the cosine of theta, and the y component is the initial velocity times the sine of theta. And so you can relate the initial velocities to the same magnitude, and then you can relate the times because those will always be the same on both sides. And yeah, so that's for any x and y with any given acceleration. Now there's a special type of 2D motion problem that is the projectile motion problem. So the projectile motion problem, we still follow sort of that plot that I set out in the last slide, but there's something a little special about these problems, which is that since it's a projectile, all of our acceleration is in the y side, and it's negative 9.8. On the x side, then, we just always use the equation delta x is equal to velocity times time. There's no acceleration in the x, it's a constant velocity. Once you find the velocity at one point in a projectile's path, in the x direction, that's the velocity the whole time. So I usually start with the x side when I'm solving these problems, and you usually won't get the answer. They're usually going to make you go to the y. But start with the x side, and then once you've written out some equation from the x motion, then you go over to the y side and do your acceleration, your initial velocity, your final velocity, your delta y, and your time. And then you'd write an equation. So if we call this step 1, and then step 2 is listing these out, then step 3 would be to do your y kinematics, and then step 4 will be again to solve the system of equations. One other thing that I'll mention at this juncture, I suppose, is circular motion problems. Particularly, so circular motion we know has a centripetal acceleration is equal to v squared over r. The magnitude of the acceleration is equal to the speed squared divided by the radius. Yeah, specifically this is the tangential speed. So if you are given a problem, which I do have some problems where you have a two-dimensional, like a two-dimensional acceleration and speed vector, then you need to ensure that you relate the acceleration, each acceleration, to the speed that is perpendicular to it. So what I mean there is if I were to give you acceleration is 4i hat minus 3j hat, and speed is 9i hat minus 12j hat. I need to make sure those numbers work. I think those numbers will work. And then I'm going to ask you to find the radius. This is an exam problem. So an old exam problem, I should say. And again, I have not looked at the new exam. Yeah, so if I wanted to solve for the radius here, I need to make sure that I relate the cross velocity and accelerations. So you'll notice that you get the same answer either way here. But in both cases, you'd use that the radius is equal to v squared over the acceleration. And so that would be either 12 squared over 4, as I've sort of sketched out here, or it would be 9 squared over 3. And yeah, in both cases, you should come away with the same answer. I'm not going to check that work. But yeah, that's your circular motion problem, and this is the circular motion that you're concerned with. The one other one that I will mention is that there's a, you'll see on some old exams, there is a radial velocity omega, and omega is just 2 pi over the period. So if you can find the time that it takes to go around 1 revolution, you can tie that into the angular velocity, and so radians per second. The only, I think, old exam problem that I've seen asked just like explicitly, it is a pretty simple calculation to find omega. Okay, I need to close some of these out. One sec. Come back. Is my whiteboard crashing? Oh, okay, there we go. Right, yes, okay, so there's two more sections left. One of them is, the first one is gonna be forces. And we've done a ton of force problems. I wanna specifically look at a few really common setup types. So first one is the block on the incline problem. So this is the other thing that I would recommend memorizing and writing down your formula sheet right away. We know that there's a weight that's directly downward, and this block is resting on an incline. We know that ultimately we want to set all of our forces so that x is parallel to the incline and y is perpendicular. And as I've done repeatedly, that means you want to split your weight up into the component parallel and the component perpendicular. I would probably memorize, I have memorized, and I would recommend memorizing, that the component of the gravity that is directed parallel to the incline is mg sine of theta. People usually say, but isn't cosine the x, yada, yada, yada. Again, this is just for the weight parallel to the incline. Just memorize this. Perpendicular to the incline is mg cosine of theta. Okay. Commit these to memory, maybe have them in your brain and then write them down on your scratch paper as soon as you start the exam, once you're done getting your honor lock checked. Yeah, and then there's a lot of stuff that you can do from here, but your approach to solving a force problem is to sum the forces in the x and sum the forces in the y. And for this type of setup, those will generally be solved independently. One other one that I want to mention, because this has shown up a few times on homework and quizzes, and this is also shown up in old exams, is the applied force horizontal to the ground. The applied force horizontal to the ground will have the same angle theta off the horizontal. So that applied force will actually split up in such a way that you will have parallel to the incline, the applied force times the cosine of theta, and perpendicular to the incline, I'm sort of running out of space here, but that would be the applied force times the sine of theta. So this can be a little confusing, that when I go to do the x calculation right here, I have fa cosine theta up, but I have mg sine theta down. Again, that's just because the angle that the weight makes with the plane of with the incline plane itself, that angle is actually 90 minus theta, whereas the applied force makes an angle of theta. That's it. That's why you have cosine for one, sine for the other. Yeah. So as I mentioned, your general practice with these problems would be to label your forces. So the one other force that I haven't labeled here is the normal force. Remember, normal force is always perpendicular to the point of contact. And then the next thing that you do is you sum your forces in the x direction. So I've already mentioned that this, for this problem that I've sketched out, that's fa, pen color, fa cosine of theta up minus mg sine of theta down. And then we set this equal to m times the x component of the acceleration. Sometimes that'll be 0, sometimes it won't. And then we sum the forces in the y direction. And in the y direction we have, for this problem, a normal force up minus mg cosine theta down minus fa applied force times the sine of theta. And yeah, now and again, you could set this equal to m times the acceleration in the y direction. I will say that for a block on an incline problem explicitly, the y is usually 0. We're not worried about lifting the block off of the incline or anything like that. If there is acceleration with the block on the incline problem specifically, I'm not saying this is a general rule, just for the block on the incline, if there is acceleration, it tends to be in the x direction. Okay, I'm just giving one example. They could angle your forces any which way, and indeed there was one on an old exam where you had a block on an incline like this, and there was a force applied like downward and a force applied upward. And maybe that the arrows are touching the box make it kind of difficult. So the first thing that I would do is I would redraw. If I were to get this picture on an exam, I'd redraw and I'd move my forces. And I'd say, oh, okay, look, they just gave me something that is going to behave like the weight and split up the same way the weight does. And then they gave me something that is parallel to the ground, just like that applied force right there. So those are forces that you know how to deal with. Cool. The other, let's see, do I want to talk about friction right now? No, so let's talk about the block on a table and a hanging block. This is also a problem that you just kind of have to do to get the hang of it. So let's say we have 1 and 2. We have 2 objects. There's a pulley or something like that. And there's a rope attached to both of them. And yeah, so, and let's, we can go ahead and talk about friction. So let's say that there is some friction, call it a coefficient of kinetic friction on the table. So block 1 is experiencing friction, block 2 is just hanging off. And they could ask you something as simple as like, what is the acceleration of, say, block 2? Okay, so let's talk about how we approach this. My general approach, first of all, is to start, let's think about the direction this thing is just going to naturally move. Block 1 is on a horizontal surface, right? Block 1 has no sort of tendency to move. The only thing that's going to move block 1 is that there's some tension pulling it to the right. And that tension is provided by block 2. The tension is also going to pull up on block 2, and it's provided by the weight of block 2. The net effect is that it's going to cause this whole system to kind of rotate like this. And so I would call this, and this is going to be kind of a different approach than you may have used, but the way that I generally teach solving this problem is to decide the direction of motion that seems most likely and to call that a positive acceleration. So for each block, for block 1, a positive acceleration will be to the right. And for block 2, a positive acceleration will be downward. Okay. So the way that this is going to translate to our actual problem solving, once we have a consistent direction for our acceleration, we can treat each block individually. So once you have assigned this acceleration direction, you can treat each block individually. So block 1, you have, obviously you're going to have our weight downward, and we'll have our normal force upward. And since we have friction, we'll also have a force of friction to the left. When I sum my forces on block 1, I'm going to do this a little bit out of order, but if I sum the forces in the y direction, I just have normal force up, weight down, and there's no acceleration up or down for block 1. So this is summing the force in the y direction for block 1. Nothing else going on up or down. So I know that my normal force is just equal to the weight, which is mg, and we should probably call that m1g. And if I sum the forces in the x direction on block 1, that's a little more interesting because that's the direction of our assumed acceleration. So that equation gives us the tension to the right minus the force of friction is equal to the m times the acceleration of the system. And again, that's m1 for the problem that I've made up here. What is our step for friction? Talk about friction, let's keep talking about it. The next step, once I have the system of equations, the next step is to replace the force of friction with mu times the normal force. So this equation becomes tension minus mu times the normal force is equal to m1 times a. And then we want to substitute in something physical for the normal force, which in this case would be m1 times g. So we have tension minus m1g is equal to m1 times a. On an exam, they likely give you the masses of the two objects and maybe ask you to say, find the acceleration. And you might be tempted to solve the acceleration right here, but you'll notice we don't have tension. In fact, the way this would usually work is that this equation would give us an expression for the tension. The tension is equal to m1 times g plus a. And that's actually the information that we would get from block 1. Then what we would do, and this is the part that's a little trickier, is then we go ahead and look at block 2. So notice that block 2, I already have the tension on it. Block 2 also has a weight downward. And what I'm going to do here is I'm going to sort of section off block 2. I know that I said downward is positive acceleration, but if I were to just do the summation of the forces in y direction on block 2, I'll have tension up minus weight down is equal to m times negative a, because that's a downward acceleration, right? So just looking at the frame of block 2, in other words, that acceleration is downward. So summing the forces in the y on block 2 will give you tension up minus m2g down is equal to m2 times negative a. That is where the direction of the accelerations comes in. Once we have set our equations up like this, we can equate our tensions. You'll notice that this gives you tension is equal to m2 times g minus a. This has to be the same tension in the rope, so I can set m2 g minus a equal to m1 g plus a, and then I can solve for a, and that's how I solve this problem. Cool. The other friction problem that you see a lot is the merry-go-round problem. Just as a reminder for the merry-go-round, for that one, since the merry-go-round is circular, you actually have that your force of friction is equal to mv squared over r. And yeah, it happens to be a force of friction. You could also do the tension in the rope when you're spinning the rope. In either one of those cases, since you have circular motion, you would set your net force equal to mv squared over r. So this is just a strict formulation of the generality mass times acceleration. Our acceleration here is v squared over r. So if I'm moving in a circle, my force is mv squared over r. All right, tight. Doing pretty well here. So the last topic is just the topic from this week's homework, the work energy theorem. There are a few problems. They tend to be pretty quick. Remember a general problem solving technique for the work energy theorem, especially if I have forces and stuff. So step 1 is going to be to find the net force, which will come from summing the forces in the x and summing the forces in the y. Step 2 is to equate the net work to that net force dotted with the displacement. Now, in truth, we can sort of peek ahead to step 2 where we're doing step 1 and say, okay, I know that my displacement, for example, we had a lot of homework problems where, for example, your displacement was all in the x direction. If your displacement is all in the x direction, when you evaluate the dot product, the y force is not going to matter. So you can just stick to the x force, right? But either way, we can always evaluate the dot product at the end of the day. We're just going to do a little bit more work than we need to do on an exam. Once we've found the net force dotted with the displacement for the net work, then step 3 is to relate that net work to some increase in the kinetic energy. Now, the one difficulty that you may have is understanding when to use forces and when to use the work energy theorem. So what I'll say is, if it is a problem with forces that is talking about an acceleration, then you'll use force calculations. If you have a problem with forces that is talking about speeds, then that is when you will use the work energy theorem. That would be my tip there. All right, I think that is like a good overview of sort of the topics as they tend to appear on exams. I would, again, recommend continuing to work through old exams. If you feel like you've done a few of them, my videos are still up on the homework if you'd like to go through those. There are likely to be a few homework problems on the exam. But again, no guarantees. I haven't looked at the exam or anything like that. But if you would like to sort of review the problem solving techniques a little bit more in depth, those videos are still up. As always, feel free to send me messages on Canvas, or you can just post in the comments underneath this video. And yeah, good luck. Final home stretch here. So good luck, everybody. And we'll see you. I'll see you Thursday still for office hours because we still have homework this week. All right. Goodbye.